Okay, so let's have a look at Chapter 10, Problems with Runout. Runout is a surface control that you typically see applied to cylindrical features or features with an axis of revolution, okay, such as cylinders like you see here. And so what I want to do is just run through some examples of how you should apply this. I think the chapter is kind of self-explanatory. It's not nearly as complicated. The runout applications, runout tolerances, are not nearly as complicated as positional tolerance, the last two chapters that we looked at. And so I think it would be better if we just look at some examples of how we can apply this. So in the first part, we have a stepped cylinder. So we have a cylinder with three different diameters. You can see diameter 562 on the left-hand side, and then 375 in the middle, and 250 on the right end. And what we want to do is we want to apply a runout control to this, or a runout tolerance to this. So because runout is a surface tolerance, we're able to apply it to a surface by using a leader. Okay, so that's one of the ways that we can apply it. And so we can just apply it like this. So what I'll do is I'll point to this surface right here and then come off of it and apply the tolerance here. Now in this case, I'm just going to do a circular runout. Okay. Not total runout, and then I'm just going to come up with an arbitrary number, 5 thou, relative to datum A. Okay, so now whenever we have runout, we always have to have a datum, right? At least one datum, typically no more than two datums, and we'll look at some examples with two datums, when and how you would use that. But in this case, basically, what A is telling us is how we are holding the part while we're rotating it. So you can imagine that we're holding the part and rotating it, and we're checking the runout of this cylinder, right? This cylinder as it's being rotated. So in this case, we're going to make A this diameter here. Now, you will notice, okay, so I'm being very clear about this. This datum is a datum feature of size, right? It's applied to the diameter, right? It's directly off of the arrow. All right, so that means it's a feature of size datum, and that's what we need in this case. So another way that we could apply this is we could apply it coming off of this extension line like so. And now, of course, this will be for another surface than this one, right? So here, we're applying it to this cylinder right there, okay? I also want to point out that there is no diameter symbol here, right? You might be thinking, well, wait a second, that's a cylindrical feature. Don't we need a diameter symbol to indicate that it's a cylindrical tolerance zone? Well, no, we don't, because the tolerance zone is not actually cylindrical. So no diameter symbols here. Okay, so we'll use the same datum. That's fine for that. And you know, they're both the same. So we can put the runout control either with a leader pointing to a surface, or we can hang it off of an extension line like we have here. Okay. Now let's move down to the bottom one here. So in this example, what I want to do is I want to first of all, let's figure out how this is going to rotate. So let's pretend this is just like maybe a shaft that's going to be supported on the left and the right with a bearing. With bearings. Okay, so we have a bearing here and a bearing here. So that means that this part in particular is going to be rotating from these two cylinders. So I want to make this A, right? But it's also supported over here. So I'm going to make this B. All right. Now, I can't say that A is more important than B or B is more important than A. So really, they are equal, and the part is going to rotate while it's being held in A and B. So this is an example of where we have a compound datum, okay? A dash B. This is where we use that A dash B. And it basically means that the datum, the compound datum, is established when we hold A and B simultaneously. All right. Now, in this example, what I'm going to do is, let's just say that we only care about the runout in a specific area on this. So we want to use what's called a chain line, which is a chain line is a thick center line, right? It looks like a center line. It's a long dash and a short dash and then another long dash repeated. It is thick. It's as thick as a visible line, right? So if you're doing this in AutoCAD, you would want to use a center line type, but you'd want to make the line weight 0.6 millimeters, okay? And then we can point to this area right there, and then that's where we're going to specify the runout. Okay, so in this case, I'll just do 0.009, and then I'm going to do A dash B, right? Because the tolerance, the runout control is, the datum we're referencing is the compound datum A dash B. Now, whenever you're using a chain line, basically what this means is that we're only looking at the runout in this area of the cylinder. Okay. But when we do this, we have to use basic dimensions to define the size of this area and its location. So we would need to come in here with some basic dimension like this, and I'll just make something up, XX. There's my basic dimensions locating it from an edge, and then we're going to use a basic dimension to define the size of it. Okay? So that's an example of a runout tolerance. Again, another circular runout tolerance applied to a chain line indicating a small area that we're applying this tolerance to. Now, I should say, what does the runout tolerance do? So what we're basically doing with a circular runout, we're basically putting, let's look at the top one up here, and let's look at this surface right here. So we can imagine that we have a dial indicator, and a dial indicator is basically a device that has a tip on it like this, a tip that goes up and down, right? It's spring loaded, and it's connected to a dial, right? And the dial has an arrow on it, and it's marked like this. And basically, when this plunger goes up and down, it's going to move the arms on this dial indicator, right? And so what you do is you take the dial indicator and you mount it to something that's fixed, right? So it's not moving. And then you hold the part in the datum. So in this case, I would hold it in A, and I would rotate it, right? And as I'm rotating, if the surface is uneven, then the little plunger is going to go up and down, and I'm going to see this arrow move. And that's going to indicate that it's out of round, or that there's runout error. Okay? And basically this says that this is the amount of allowable runout error, in this case 5 thou. So I can have total needle movement of 5 thousandths and no more. All right. Now that's circular runout. So circular runout is when we measure, and we measure it at one point and we rotate it around, and then we stop, and then we move this over here and we measure this point and we rotate it around like that. So you see what we're doing each time is we're tracing out a circle, right? And that's why it's called circular runout. Now, if we change this to total runout, which is the double arrows like that connected, all right? Total runout means that we're going to be rotating it, and as we're rotating it, we're going to make a circular pattern, but we're also going to move the dial indicator left and right, so it's going to move across. So we're really going to trace out something that looks like this as we're moving along, and that's total runout. Okay? So those are those two examples, right? Let's look at a couple other examples here. All right. So in this example here, we are, again, going to do another example of the runout applied here. Okay, so again, let's just do the runout. And let's say we want to control the runout on these two surfaces as the part is rotating or being held in this larger diameter. So this larger diameter is going to become my datum, right? And remember, we have to associate with the arrow right here. And then I can just point to that surface, and I'll call this out with a circular runout of 6 thou relative to datum A. Right? And then I could also come down here and go like that, right? So I can use this to have two arrows come off, provided, of course, that it has the same tolerance specifications in the feature control frame. All right, so that's an easy one, right? Let's look at this other one down here. Now, on this one, we want to control the inside, this hole, right, as it's being held and rotating in this part. So this is going to be my datum feature of size A, right? And again, it's associated with the arrow here. But what I want to control is I want to control this hole, right? That's a hole. I want to control this hole, right? But I also want to control this surface here. So can we control that surface? Well, we can control it with a circular runout, okay? So to control this inner part, all we need to do is point to it, right? Kind of easy. And we say, let's say, circular runout again, 0.010 relative to A. Okay. We do the same for this one right here. So we could come down here like so. And then let's give this a different number. Again, relative to A. And don't forget your arrowhead. So how do we do it off this part then? Well, you can kind of see the extension line. We're going to have an extension line coming off here. Now, you might not have known this, but you can have an extension line that's not associated with any dimension, right? An extension line is just how we kind of point to or indicate a surface, right? So we're indicating this surface right here. The only thing we can do here, we cannot do a total runout for this one. So this one we could do a total runout. This one we could do a total runout. But this one we can't, because as we're rotating it like this, we're going to hold, again, the dial indicator, we're going to hold the dial indicator, we would hold the dial indicator steady like this, right? And then that would trace out a circle. Once we start moving this, we can't really measure the deviations around the axis. And that's what runout is, deviations from the axis of rotation. All right? So here, we could only do circular runout. Like so. Okay. I should also mention, for runout, there is no material modifiers. So no LMC, MMC, no RFS. Okay. We also can have no material modifiers here. MMB, LMB, RMB. Okay. So, you know, no kind of tricky things here, right? And again, still no diameters. All right. So let's do another example here. Okay. This is our last example that we're going to look at. And on this one, again, we want to use a compound datum, right? Because in this example, we're going to say that we have a bearing here and a bearing here that are holding this part while it's rotating. And bearings provide the most common sense method for establishing where the part lives. Remember, datums say where the part lives. And if we have a bearing here and a bearing here on the left and the right, that's where this part lives in the machine or mechanism. So here, we're going to say this is datum X. We're going to say this is datum Y, right? And now, what do we want to control? Well, let's say that we want to control this face right here, right? So we could come off of here with a extension line, go up like this. It's not possible to use total runout, so we got to just limit ourselves to circular runout, 0.007, and then x dash y. Okay, let's make that a little bit better. Now, if we wanted to control this surface right here, the surface of the cylinder here, we could point to it like so. Circular runout. We could also do total runout here, right? It's possible. 0.007 x dash y. Okay. Last but not least, we can do surface, right? So we'll do a surface again. Let's say we want to control this surface. How is the part being held? Well, it's being held here. So we're going to make that our datum. And then let's say that we also want the part to be held. So it's going to rotate here, right? But it's going to be fixed against a face here, right? So it's not going to be free to move this way. It's going to be held against something. So really, this is an example of having two datums, right? So the part is going to be held here and fixed here. Now, I can give you an example. Of how we might use that. So we can see in this part right here, right? Just the A would hold it here, right? But in that case, it's really free to move here. There's no constraints against it moving to the left and to the right. We're only saying it can rotate. But if in the actual machine, it's being held up against something, like this part right here, right? It's not free to move this way. So we want to add the second datum, right? That is on this face right there. And that represents where the part lives, right? So we've represented that here. And now we want to control this face, so we could point to this face and say we want, remember, we can't do a total runout. We have to do a circular runout here. And we come up with some number, let's say 7, and it'd be A, B. Now notice here, this is not a compound datum. Let me get this up a little bit. Not a compound datum A dash B. Okay, so that's important. This is the primary datum. This is the secondary datum. Right. So with runout, we can have up to 2 datums. You can imagine that we can't have 3 datums because it's still, the part needs to rotate. In all of these examples, the part really needs to rotate. All right. So this is one of those cases where we can't constrain the degrees of freedom 100%. Like we can, for example, with this, right? So this part right here, it's not moving when it's functioning, all right? So it's going to be held by the bolts or whatever's down here. But this part, it's designed to rotate. So we need to let it rotate through our datums. All right, So I hope that will give you a good idea of how to apply this in the problems. This is actually, I think in the past some students have expressed that Chapter 10 is kind of a nice breath of fresh air after Chapter 8 and Chapter 9, which were kind of heavy, a lot of rules with positional tolerances, a lot of special cases and considerations. So this is a good opportunity for you to get a good grade on the quiz and on the application problems and the review questions. So make sure if you have any questions, send me an email and let me know if I can help you in any way. All right. Thank you.